All right, we're going to go ahead and get started. First off, can everybody hear me? All right, excellent. My name is Tracy Schaefer. I'm with KIT Communications, and the topic of our webinar today is Erate submissions and planning tools for Erate 2016. Topics for today is design considerations when designing your system, design tools, so what's out there available to help you design your system, and using PEPPM for Erate purchases. So to kind of back up a bit, as simple as this may seem, I wanted to define what Wi-Fi is, which is it's data communications using radio waves. And for the purposes of our discussion today, we are going to be talking about the 2.4 gigahertz range, which is the ultra high frequency range, and the 5 gigahertz range, which is the super high frequency range. Okay, so moving on to wireless design considerations, we're basically going to design for three major components. We're going to design for device density, we're going to design for geographical coverage, and we're going to design to minimize interference. So first, looking at device density, we're looking at the quantity and proximity of devices to each other. So we have, in this first scenario, very few users in this space, and everything works great. But what happens to your network or your wireless when we move to this density and we have a lot of users, a lot of devices concentrated in a small area? So we need to make sure that when we design with this consideration in mind. We also need to design for geographical coverage. So we're basically designing with the idea of trying to cover as much of the airspace, the physical space in our facility as we possibly can. We want to get radio waves to all the areas that potential clients and users would be accessing our wireless networks to. So to kind of understand the geographical portions of this, we need to first kind of look at what a radio wave looks like. So here, we look at a radio wave. The wavelength is determined by the center of peak to the center of the next peak of the radio wave. So that is the wavelength, and as you see in the 2.4, this radio wave in the 2.4 is much more linear than the radio wave of the 5 gigahertz band. And when we talk in frequencies, we're talking about the amount of times that this wavelength passes a single point. And as you can see, because of how close these are together, there's a lot more of those passing a single point in time than there is in the 2.4 band. So this is a higher frequency just because of how much tighter these waves are to each other. Now the reason this is important to understand is because when you're designing your wireless for your facility, you're going to have a lot of construction and building materials, things like that, that are going to affect these two signals. So everything has a density, and things like a wall, which could be concrete, could be wood, but assuming, let's say it's a concrete wall, it's very dense, tightly packed. This more linear wave here is going to have a little bit easier time penetrating through that wall than this 5 gigahertz radio wave. And as this passes through, it's going to have less resistance, which means more of the signal is going to propagate through it versus the 5 gigahertz. And if we look at that compared to, say, glass, here we have the same two waves with a less dense wall. Obviously, for both of them, there's going to be less interference in the wave for it to pass through. So lastly, we have to design with interference in mind. We want to try to minimize interference as much as possible, and there's two types of interference: RF noise and co-channel interference. RF noise is measured by signal-to-noise ratio. which is the range from the noise floor to the receiver signal. So if we think of noise floors, we could have two possible analogies here. We have a rock concert with thousands of people screaming and yelling, very loud, but we also have a library where it's very quiet. So if we consider those two to be equivalents of our floor, possible floors, noise floors, we can see that the ratio is different from this to the receiver signal. So when we think about it in terms of humans talking in these spaces, if you have somebody talking, they don't have to talk very loud to be heard in this scenario. And the louder they talk, the higher the differential or the ratio between the floor and how loud they are, which means they're just easier to hear. When we go to this scenario here, the noise floor is so much louder that even when they're talking loud, there's very little differential, which makes it very hard to hear. So obviously, in your facilities, this is the better noise floor to have than this, and we'll talk here briefly about how to affect change on those. So one way you can minimize is to know what gives off RF noise, because these are the interference pieces within your network. We have microwaves, we have cordless phones, other wireless access points, Bluetooth devices, wireless microphones, and if you're in a school and your students are bringing phones, cell phones are probably one of the bigger devices or culprits bringing noise floor, or raising your noise floor. We also have co-channel interference, which is two radios broadcasting on the same channel within the same airspace. This is a very understated problem. A lot of Wi-Fi manufacturers haven't mastered dealing with it yet, and so they tend to kind of minimize what the effect is on your wireless. And unfortunately, as we are moving to AC Wave 2, it's only going to get worse before it gets better. So first of all, to kind of understand this problem, we have to understand that 802.11ac adds more capacity through wider channels. And we get wider channels by bonding 20 megahertz channels together to create 40 megahertz, and then bonding 40 megahertz channels together to get 80 megahertz channels, and so on. And these bigger channels give us more throughput for data. So if we look at the actual channels, what we see is this is the 2.4 band that we talked about earlier in the beginning, kind of blown up here for you to see. And within this band, we've subdivided it into smaller bits, which are the channels we're talking about. So we have the center of frequency, we have the bottom of the channel, and the top of the channel, which is just basically representing the whole size of that channel. And if you notice, channel 1 overlaps channel 2 overlaps channel 3, and so on. So we have a lot of overlap here. With 2.4, we have 13 total channels, but only 3 of them are non-overlapping channels. 14 is not usable here. It's only usable in Japan. And 2.4 in general is reaching end of life. Everything is moving to the 5 gigahertz band. Your non-overlapping channels here, as represented in red, are 1, 6, and 11. So if you ever dealt with wireless, you kind of probably heard those 3 channels. And that's why those 3 are recommended to be used, because they never overlap. So if we look at the 5 gigahertz channel, we move up to 25 channels, which sounds great. You know, we have 25 channels to work with. But these are 25 channels at 20 megahertz. And we run into another problem with the 5 megahertz channels. We have something called DFS. And DFS is dynamic frequency selection. It's reserved for radar signal. And unfortunately, it gets priority over those channels over your clients and devices. So anytime it senses something within its frequency range, your system is designed to drop its clients and duck to allow that signal to get priority, which means if you're using those channels, you are risking having that system drop your clients. So if we look at the 20 megahertz range, you can see here we have 8 non-overlapping channels to work with, which is great if we don't assume that we're going to use DFS channels. So plenty of channels to work with there. But now with 802.11 AC, I mean, you're moving in the direction of combining these channels, which means we are combining to 40 megahertz channels, and now we're down to just 4 non-overlapping channels, excluding the DFS channels. But it gets worse because we then move to an 80 megahertz channel, and we only have 2 non-overlapping channels if we exclude DFS. And then even worse, we move to the 160, and if we exclude the DFS channels, we have 1 non-overlapping channel. So since co-channel interference is a problem that's a lot of times hard to visualize, we decided to use a little bit of an analogy here to kind of explain this process. So here we have a client, and we have 2 access points in the competing airspace talking to this client. So in this scenario, our client, if both these access points are talking, both these individuals are talking, the client can pretty much tell which one is which, because the frequencies at which they're speaking, their voices, are different enough where he can tell which one's which. So if we apply this to access points, each one of these individuals represents an access point, and they represent a bonded 40 megahertz channel, so two 20 megahertz channels bonded together. We have 36 and 40 represented by this gentleman. We have 149, 153 represented by this young woman. We have 44 and 48 represented by this young lady, and we have 157 and 161 represented by this gentleman. All unique individuals, so they're all speaking at the same time, but our client still has a chance to be able to figure out which one is which and which one to listen to, because all the voices are still different enough for them to be able to kind of figure that out. But watch what happens when we go to 80. So we go to 80, and now we're talking about 4 devices all within earshot of each other. And to the client, 2 of those on each side, 2 of those APs sound the same. So we have these channels bonded together, 36, 40, 44, and 48. And we have 2 of those APs, so they sound identical. And over here we have 149, 153, 157, and 161 bonded together, and we have 2 of those individuals. So the client is here trying to listen to all these signals, and to make matters worse, basically out of 4 APs, 2 of the signals on each sound exactly the same, making it much tougher for our client to figure out which one's destined for it. And even worse, if we move to 160, guess what? Everybody sounds exactly the same. Now the client has to try to figure out which client is speaking to, or which AP is speaking to him, and unfortunately they all sound exactly the same. Now, it is a real problem, and as we'll see in a slide later, you can see the effects of it to some degree through wireless surveys. But if we first look at how we typically handle designing our networks, we can see the inherent flaw here. So typically when we design a network, we draw circles on a map, and we guesstimate exactly where we want our APs to go based on space. But we really don't know how to control the wireless signal. So when we first designed this, we put the APs in, and the signal, we create this pocket here, this crossover, and that's where your co-channel interference is going to happen. So the devices in here are falling into that trap. If you're an AC and you're only using 80 or 160 bonded channels, you're going to have problems because these people are going to be faced with that challenge of trying to figure out which signal to listen to. So then inevitably, to fix that problem, you're going to back it down. And you're going to go to your AP, you're going to go into the antenna, you're going to turn the antenna strength down, and you're going to guesstimate what that should be. And then we're going to create a secondary problem, which is we're going to create these pockets where these clients are sitting outside of our signal range. And then we go through this vicious cycle of turning up and down our antennas, all guessing at what we need to do to cover those areas. So if we take our analogy and we apply it to the same building, at the 40 megahertz, in a one-to-one scenario where we're putting APs in every room, there's enough variety where even though we have to duplicate some of these individuals, they're far enough away from each other where they should barely be able to hear each other. So a client sitting in the middle here should be able to discern which one based on who's louder. So when he's over here, he's going to be loud. This person's going to be louder, so he's going to know that that one is his signal versus this one. Down here, it's even better because we have enough variety where we're not even duplicating. Now we move up to the 80 megahertz, and now we start to see problems. So we have to duplicate. We have 4 of this young lady, and we have 3 of this gentleman. So any clients moving around up here are hearing pretty much all the APs, but they don't know which one because they all sound almost the same. Down here, still bad, but because we have not as nearly as many APs, not quite as bad as up here. But then we eventually move to the 160, and that's when things get really bad. Everybody's yelling and everybody sounds exactly the same. So how is your client going to know what to listen for? So the way we solve all this is with design tools such as wireless surveys. So what is a wireless survey? It's data collection. So we are collecting data from your facility to ascertain signal strength to each access point, channel assignments, and background noise. And with that data, we are generating heat maps, which then represent visually signal strength, signal to noise ratio, channel coverage, and identify potential issues with weak signals, signal to noise ratio problems, channel assignments, and channel overlap. One type of survey is an AP on a stick. And an AP on a stick is basically we take an AP, we put it on a tripod, and we move it throughout your facility, and we measure the air to see how that signal is propagating throughout your facility. It's definitely a very time-consuming and expensive process because you can imagine the time it would take to unpack an AP, get it out, hook it into your network, and then move it throughout your facility and measure the wireless as we move it from place to place to place, and then go around and take readings in that area for each place we move it. So, it's definitely the more expensive and time-consuming type of survey to do. When we normally do our surveys, we've already said, we basically are estimating the coverage, not really based on any science, but just our visual understanding of the space we have to cover. The problems with that is it doesn't account for the walls and the density of the materials that the signal's got to propagate through. It can't show you how the signal is actually declining over that space. And you definitely can't see the channel overlap that's going to happen as a result of having those APs in their locations. While wireless surveys do have a cost, the real question is, does that cost actually exceed what your costs would be from not doing one? So some of the costs that are hidden with not doing wireless survey are that you can oftentimes over-design this and put too many APs in, which means you're buying APs you don't need, and it also means that you are you're potentially worsening your performance by creating more channel overlap. You can also go the other direction and put in too few APs and not have enough coverage, and now you got to go back to your superintendent or your board and ask for more money, which nobody really ever wants to do that. And as far as the channelization goes, you know, with the wireless survey, you can really come up with a good channel plan, because if you don't and your channel plan is bad, you're going to have all those co-channel interference issues, and you're going to have a brand new system that your superintendent and your teachers and your administrators are all looking at you going, hey, we just spent all this money to get this new system and it doesn't work. That cost is almost priceless to avoid. So another type of survey, since the AP on a stick is a little bit more pricey, another option would be predictive planning. It's kind of the compromise between the two. And basically what we were doing with the predictive planning is we are making a whole bunch of scientific assumptions and guesses based on what we know from lots and lots of wireless surveys as to how that signal is going to propagate out. And give us an idea before the install of what things are going to look like. So if we look here on our traditional guesswork model, we are just putting these two APs in and we're just assuming it's going to cover this whole area. We don't really know much else. But if we go on to this map and we did the predictive planning, what we can start to see is these concentric rings. So we can start to see how the signal is going to be affected by the walls and where it's going to start to die off. So this gives us a lot more detail about our signal for planning purposes than this map does. It also shows us where the overlap's going to happen, where we need to start looking at potential co-channel interference issues as well. So a lot of visual representation of what's going on here. So if we look, we have the scenario where we have concrete walls and drywall interior walls. So with predictive planning, we're putting these scenarios together. We're looking and we're seeing that these two access points in a concrete wall scenario, they're going to start dying off very close to the center of the AP. We might cover one room each with a little coverage in the middle, but after that, we really need to start coming up with a different plan. On the drywall side, we can see that we actually get more coverage. So this would completely change our design considerations when we're talking about drywall versus concrete. You know, here we're going to have to invest a little more money in putting more APs in. Here we may be able to just get away with one AP kind of in the middle and be done. So this is a really good illustration of where predictive planning can help save costs and give you a better design. We can also break out our results from the survey into the actual wireless band. So here we're seeing the 2.4 and the 5 represented. So same 4 APs, but you notice that as we sort of predicted before when we talked about the 2.4 and the 5, the 2.4 with its more linear wave has a lot wider propagation capability than the 5. So in this wireless survey, predictive survey, we can see that the 2.4 is filling most of our airspace, but the 5 antennas from those same APs are not covering nearly as much. So what we run into is, you know, how do we control both antennas to make sure that we're not over covering some and under covering another like we would have here? We would have to maybe add other APs, but then we'd have to back down the 2.4 to make sure we're not flooding the noise floor here with more 2.4 signal. So this is where this tool would be great in showing you how to properly affect the change in power, which antennas to broadcast off of to make sure that we get the right balance of 2.4 and 5 gigahertz. So we run into the problem of, hey, we got bad coverage, so we're going to just throw another AP in. That'll take care of it. So we have a problem. Client up in this area was having problems, so we throw another AP in there to solve the problem. But if you notice what the wireless survey is telling us is we've actually created a lot more problems. So that single AP in there, the co-channel interference functionality of it, because we're 36 on the new one and we've got 36 here, or 40 on the new one, and we've got 40 here and here. So all these are creating co-channel interference, increasing the noise floor, and now we've actually ruined our coverage by just throwing that AP out. So the nice thing about these surveys is they represent everything visually in color, so we can really kind of see and understand what's going on. And what we have here is signal to noise ratio, so we can kind of see, you know, how that's playing out, where our noisy areas are and where our quiet areas are. And then we also look at channel coverage, which this is a great feature for co-channel interference because it's gridding off the map area and it's showing where effectively your channels end in the air. So we have this nice little pocket here between where we're not seeing the two channels intermingling, so we don't have to worry about necessarily any co-channel interference, but we do have to maybe look at how do we cover, make sure that has good enough coverage, which we are because we're getting that from this, this AP right here. So this is a great way of really seeing air and seeing what the channelization looks like. So we already talked about predictive planning. That's probably your best tool. And then we have the active system wireless surveys, which can come in the form of the AP on a stick, which, you know, we've already talked about. That's a little expensive, probably not the best way to go. But we can do an active survey where we are going in and basically surveying your airspace with your existing wireless to give you a real-time you know, view of your network and how it stands so that you can make informed decisions on how to correct those problems. So what we would typically do is combine both. So if it was a new deployment, we would come in, do a predictive planning survey. That would give you your quantities and initial placement of APs. We would then come in and install the system. Once the system is up and running, we come in and do an active survey. We would see if the predictive plan matches up with the active end results. If it doesn't, then we would just make the minor changes that we need to cover any potential issues, and then we would survey those areas again, and hopefully that would take care of all the problems, and you're up and running with the correct amount of APs and with the maximum benefits of your new deployment design. So lastly, we want to talk about actually going through the E-rate purchasing cycle. You have a couple options for submitting for E-rate funding. You can do a 470 request with public bid, or you can do a PEPPM mini bid. The 470 request with public bid, it's a little bit more cumbersome. You'll have to fill out the 470. You'll have to issue an RFP. You will have to make sure that it is available for at least 28 days before they consider. You will have to have a sealed bid process. You'll have to advertise in 2 local newspapers for 3 weeks. So there's a lot of things that go into that you'll have to do before you can actually get your bid for submittal for your funding request. And on top of that, you know, you're pretty much stuck with the low bidder. So you don't have a lot of control with this on top of all the work that you put into it. Another option would be to use the PEPPM contract, which is run by the CSIU. So with the PEPPM contract, since these lines have already been bid, you have a lot more flexibility. You can completely skip the 470 and bidding requirements and conduct a mini bid. And to do that, you basically have to go on and look up the categories for the products that you're looking to bid, and you construct a email that would be, here's a sample with a whole bunch of the jargon that goes into it. Your E-rate rep should be able to give you or E-rate consultant should be able to give you a copy of this that you submit out for bid. But the nice thing is that you can use things like price, proximity of vendor to work location, past history with vendor, any number of criteria you can use to weight how you want to weight the bid. So it doesn't have to just be price, which really at the end of the day gives you a lot of flexibility there. So another issue that we ran into last year is, as a part of the mini bid, we have this template that was pushed out. So this template has the building location, self-explanatory, the PEPPM category. So this is the category that if you're going to push out your mini bid, the wireless portion of your bid has to be forwarded out to the contacts for all the wireless vendors on PEPPM so that they can bid on this. You would put the manufacturer, description, if you're talking labor or materials, and then the model numbers, and then your estimated quantity. Now, there was a lot of problems with this last year because there was kind of a misunderstanding of how to properly fill this out. So we have this incorrect method where in school districts not knowing how to break these products out or what went into them, they would make these line items for all the installation and parts to run the Cat 6 lines. The problem with this is when you go to submit your funding request, you are buying a whole bunch of products as a part of that. So you need to have those parts broken out in the proper quantities for that purpose and for the purpose of making sure that your bid is coming back with the correct parts. So we have this scenario where we're saying Cat 6 cable runs, but do we know that that's Cat 6 riser or plenum? What about the patch panels? What about the face plates, the connectors, the support structure? All those pieces are missing, so you could inevitably get a vendor who bids on this and doesn't even include a lot of those things, and you win the bid or they win the bid, you move forward with them and you get to installation time only to find out then. So it's important to break these items out and get accurate counts so that you're getting apples to apples bids and you make sure that what the people are bidding is actually accurate and complete. With that said, that basically ends the educational portion. We would, as a company, would like to let you know that we do obviously wireless design and predictive planning. We have engineers and do a lot of these surveys for schools and the private sector. So it's definitely something that we're very good at and can offer for you. We also do E-rate mini bid material lists and prep. So one of our services is to come in to your facility and generate those lists of materials that we talked about in the mini bid so that you can send it out for bid with the correct material listing in place. As far as wireless for E-rate season, we are a Cisco Meraki partner, a Ruckus Wireless partner, and a Fortinet Maru partner. In case you might not have heard, Fortinet, a $3 billion a year company, bought Maru to incorporate their wireless into the Fortinet firewall products. So that is a great partnership, which I predict is going to really grow strong off of Maru's really good solution for co-channel interference. Ruckus, I'm sure everybody's been familiar with this and beat to death with that product line. Great product line, great for geographical coverage. And Cisco Meraki is great when it comes to cloud, and of course it's got the Cisco name. So we can help you on any one of those product lines. We use each one to fit the right situation. So if you have any need for any of those, please feel free to get a hold of us. All right, any questions? To my knowledge, that the question was, there's a PEPPM related webinar coming up, which is going to have kind of a review of how this mini bid process is going to work this year. And I do not know at this point if there's any changes. The meeting for the resellers is coming up. So I will kind of know after that if there's anything that's changed on this since last year, and if there has been any changes, I will make sure to send out a follow-up email to update everybody. Any other questions? Yeah, the E-rate planning services, we don't have like a menu type price for that. You know, basically it's square footage for the surveys, it's you know, the number of buildings, number of lines, those types of things will determine what we charge to do the E-rate prep services. So that would be something, if you're interested in it, just shoot me an email or give me a call, and we can we'd be happy to come out and do a free quote so you can see whether or not it would be something you want to pursue. But it does make life a lot easier for filling out your funding request when you have that nice completed material list off of that mini bid form, because everything translates really well over into the 470 request submission, or the funding request. Any other questions? Yes, I recorded this, so I will send this out as a follow-up to everybody so that you have it if you need it for any future reference. Anything else? No? Okay. All right. Well, on behalf of KIT, I appreciate everybody attending, and I look forward to hopefully working with some of you, and good luck in your upcoming E-rate season. Thanks.